Well, we can also use L'Hopital's rule when we're calculating the limits if we can convert our function of n to a function of x. So let's suppose I want to figure out if the sequence n over 2 to the n converges or diverges. Well, I can put an x in there and get a function of x over 2 to the x, and now calculating the limit as x goes to infinity, this is an indeterminate form of type infinity over infinity, but I can apply L'Hopital's rule, and that says that the limit is equal to the limit as x approaches infinity of the quotient of the derivatives, and that's 1 over 2 to the x times the natural log of 2, and now it's easy to see that that limit is 0. So the sequence actually converges to 0. Now what happens if the limit as n approaches infinity of an is infinity? Then we say that our sequence diverges, but this diverges with a particular pattern. It diverges to infinity. So we can give more information about how it diverges by saying it diverges to infinity. The limit, to be more precise, as n goes to infinity of an equals infinity, means that for every positive number m, there's some integer n with the property that for all integers bigger than that n, the values of the sequence an are bigger than this very large number m that I chose. And I can choose any large number m that I like. It could be 1,000, 1,000,000, a Google, but whatever it is that I choose, there is some point in the sequence so that every term in the sequence from that point on is bigger than the number I've chosen. In other words, the terms of the sequence grow without bound, and in this case we say the sequence diverges to infinity. Or we might say the limit as n goes to infinity of an equals infinity. And notice that if the limit as x approaches infinity of f of x is infinity, where f of x is some function that we've created by replacing n by x, then the limit of the sequence is also infinity, or the sequence diverges to infinity.